Let me give you a quick overview and in my mind a really good mental picture of hypothesis testing and statistical power. Let's clear out some jargon. H naught is null hypothesis, namely for most of the time it's a control group. H1 is alternative hypothesis, usually is a treatment group. And p-value is a probability of the observation is what the result is greater than the observation and under the expectation of null hypothesis is true. Put it in plain word, is a probability assuming H naught is true. The observation of a result is at least as extreme as what you observe. It's almost like put into a graph. It's like if see this is a distribution, the p this is a v this is a z observation, and then the p-value will be the red shaded area. So for the alpha, and that's a two parameter that determine. This one is you calculate after the experiment. I'll talk about that later. Alpha is a probability of a type 1 error, or in other words, rejecting H naught if H naught is true, or just a probability of a false positive. Put in the word is the green shaded area is pretty much if what the probability of you rejected H naught is true, but you still reject H naught, which is the area here. And the beta is type 2 error is pretty much a probability of a false negative. It also is a 1 minus rejecting H naught when H naught is false. So effectively you can say it's fail to reject H naught when H naught is false. And that conversely is the red shaded area. And so in the experiment, you set up alpha and beta before the experiment for your tolerant for type 1 error and type 2 error. So you're tolerant for false positive and false negative. And then you, after the experiment, you calculate the p-value and then compare with the experiment. If the p-value is less than alpha, then you reject H null hypothesis. If it's greater or equal to alpha, you say fail to reject H null hypothesis. Keep in mind, very, very importantly, it's not equivalent to not accepting H naught. It's failed. It is not equivalent. So it's So let's look at the mental picture, which is my favorite part. So here is a distribution of the null hypothesis with mean of mu naught, standard sample standard deviation sigma, and overall will be sigma naught square over n naught, where n naught is the total the sample size. And for alternative hypothesis, mu1 square over n1. And the shaded area, just assume though both are normal distribution. You will have beta, which is a red area, is integrated from negative infinity to c. C is a critical level which you set. Since the formula of phi x is exactly this, you just need to normalize it back to the standard normal distribution, then it will become phi c minus mu1 over sigma 1 divided by square root n1. Similarly, calculating this will be 1 minus phi c minus mu naught divided sigma naught over square root n naught. You got those two equations, and then you can use this. This is effectively just a definition, phi z t equals t. Then you can express those two equations in terms of z. Then z1 minus alpha equals c just like this. Just this. And then z1 minus beta, this equals negative z beta based on the definition is obvious, because this part plus the other side is equals to 1, and thus you got this. You got this, and then you combine equation 1 and 2, eliminate c, you will get this equation, and you can pause the video to derive yourself. It's pretty trivial arithmetic algebra, and you'll see this equation cannot be it can be further simplified if you assume sigma n1 n equals n1 plus n2. You can also further simplify by creating a factor, if you want. That's for your own pleasure. You can do n1 equals n1 over n2 equals r, just for the ratio, and then you can further simplify this equation using this. It will be a little bit more complicated expression. We can derive it if you feel like wanting to derive non-equal sampling. But you will get this equation. It's an effect. It looks nice and neat. Requires sample size. So n equals sigma squared z1 minus alpha plus z1 minus beta squared over delta squared, where delta is mu1 minus mu0. Intuitively, this is effectively how much sample you need to get desired desired confidence based on the power analysis. It's very intuitive. This derivation seems daunting at the beginning, but it's very trivial. If from here this distance is z minus alpha normalized. So because this is alpha, this area size is alpha, so this area is 1 minus alpha. And then you need to normalize it back to this shape. Then you need to multiply with sigma divided by, you need to widen it by the width. Similarly, this distance is z minus beta sigma 1 divided by n square root n1. And then the distance between those two will be compared with mu naught minus mu1 minus mu naught. So effectively, though this plus this equals the distance, which is exactly this equation. You can use this graph to arrive to this equation instead of this derivation. You will reach the same conclusion. So what are we? I want to talk a bit more about this graph. So as you can imagine, alpha increase will lead to, because alpha increase, this area increase, it will move the bar on the left side, beta will decrease. It almost always have an opposite effect. Like, of course, given the sample size difference. Of course, if you reduce the n, different scenario. Reduce n, the alpha and beta will both reduce because both of these will become narrower. And you can see from here as well. And yeah, this is I think the very good mental picture. I think if you forgot everything, just remember this graph will get you, like, you forgot every concept of hypothesis testing and statistical power. Remember this graph can get you back majority of the knowledge, just of those, like, just to reiterate, H0, null hypothesis, alternative hypothesis, give a critical level. The right hand side triangle, kind of triangle is alpha, left hand side is beta, and then distance is delta, and then again, critical level is the boundary between those two, and then you can shift back and forth, and the width scale inversely with n, and proportional to the sample standard deviation, and then that will resulting, those add together equals delta, will resulting into the required sample size formula.